Hello everyone, how is it going? Welcome to part 3 of this course. Here we are trying to achieve advanced lane detection. If we go back to our previous courses, we did the simple lane detection where there was a straight line, a straight path, and using canny edge detection followed by hook transformation followed by averaging, we were able to identify the approximate position of the lane. But that this scenario is good as long as the road is a straight road and you're just going in one direction forward. But if you were to come across a curvature in the road, a turnabout in the road, or if there's any kind of movement in the lines, then this algorithm would fail and it'll be difficult for us to understand the curvature of the road. So for that purpose, we are introducing this new topic on advanced lane detection. And before we go into the topic, we need to understand a few basics. And one of the basics is about camera calibration. So let's understand what this is and what camera calibration involves. So you're basically trying to calibrate the camera vision sensor and to make sure it's giving us the right information about the surroundings. So the way a camera works is very similar to how our human eye works. And human eye is able to form an image which goes back into our retina, which is the back portion of the eyeball. Similarly, the camera also forms an image in the back portion of the lens, which creates the image and then processes it for us to use. Now, the one difference between a camera and an eye is we have two eyeballs, and both of these eyeballs play a major role in understanding the perspective of the vision. So it can understand the two eyeballs are separated in a way that you can identify or understand the depth of or the perception of the vision. So you can understand how far an object is or how far this object on the right hand side or the left hand side is. So even though the object is not in the exact vision, it can, because of two eyeballs, you can understand the depth or the location of the object much better. However, camera is dependent on one pinhole lens, which is just taking the image of the object that's in front of us. But anything which is on the curvature or on the sides of the camera, it becomes very difficult for the camera to capture the exact perception of the object. So what happens is it ends up into something called as distortion, and you can see how these images look like. I think this is a very good article. This is on Medium, and it was by this gentleman. I'll put it in the description for you to read. And he has explained it in a very pictorial way for us to understand. So this is the original image, and if you look into the distorted images, let me maximize this a little bit. So you can see these are the different types of distortions that can occur. So look into this particular picture. The whole frame has distorted. In the same case here, the frame has also been distorted. And for that, and if you look into this major problem here, if you try to bring that image into this format of our rectangle, and if you try to stretch that image, so that's how OpenCV we will be reading those images. And this is how this distortion will affect the image. You can see on the edges, you can see this edge over here. So it does affect the image quite considerably. And this causes major problem when you're trying to do lane detection and trying to identify objects in the real world, especially if you're trying to run a machine using that, or depending on your detection, you have a machine running. So that comes into a major problem, and for that purpose, we are going to use something called as camera calibration to help resolve this problem. So one way of doing this is understanding how much distortion is occurring. So every camera is different. Every camera uses a different type of a lens. It is made up of a different property. So every camera behaves in a different way. And for that purpose, every camera has its own level of distortion, and we need to understand what is that level of distortion so we can undistort the image when we are using it for image processing. So for example, this is a trapezoid, and especially with these cameras are these side mirrors are a very good way of explaining how the image affects. So if you look, if you notice in your vehicle the different side mirrors and or the mirrors you have in the car, each mirror reflects the objects in the background in a different way. What I mean by that is each side mirror is formed in a different way, and you will see the objects in the mirror, or you can perceive these objects in a different way. So when you go into the car next time, visualize this, and you can see the difference between the different mirrors that you have in the car. In some mirrors the objects look much further, and some mirrors the objects look much closer, and this is all because of this phenomena. So we need to understand what this distortion is, and for that purpose computer vision has a very good algorithm, and this is based on something called as a chessboard detection. So the property of a chessboard is it has symmetrical shape. So it has symmetrical number of the size and the width of the black squares and the white squares are symmetrical, and it is of very high contrast. So it's very easy for a camera to detect the white boxes and the black boxes. So for that purpose, for camera calibration, chessboard pieces are very good to be used. So what the camera does is, now with that same camera that you're going to be using for lane detection, you're going to use that camera and take a bunch of images of a chessboard, and then try to understand how much is the real, because in reality that your chessboard is of symmetrical shape and it has equal width and height. But if you go and process that image into your camera and then see what's the exact measurements between these boxes, then you come to know that how much the image has distorted your chessboard. The chessboard, which should have been a symmetrical shape, will be of different shape or different distortion after taking it through a camera. So that will give us a good understanding of how much distortion is happening because of your camera. And once we know that property, then we can use that to undistort an image. So you just reverse that property. So if you understand how much it's warping itself, you can in the next stage we'll see how we can nullify that effect by just reversing the effect. So let's come back to our code here, and so far we did the simple lane detection, and we'll open up a new code. And for this purpose we are going to be using a simple chessboard, and I have it on this page here. I'll put the link in the description for you. We'll just simply do copy link, and we'll come back here and then paste this link. And for us to download the image, there is a command called wget. So we just wget, and for that purpose we need to just specify that you're going to be downloading it, and you specify the file name. The file name here is chess.png. So we'd say chess.png, and then paste the link that you copied from the GitHub repository. So in this case, just for the purpose of this tutorial, we used some random chessboard image off of the internet. But in reality, when you're doing your lane detection, you want to use your same old camera that you're going to be using for lane detection to take the images of this chessboard. Once you have that, come here and just download this, and it'll take a few seconds and download the image for us. So it looks like it's downloaded, and if you open up the directory, you can see that there is a chess.png available for us. So good. Now the next step is to understand how we can do the calibration aspect of the chessboard. So for that purpose, let's import our OpenCV, and we're also going to be using Google Colab's CV2 show so that we can display the image right here in the browser for ourselves. And we say from google.colab.patches import something called as CV2 show, which is going to help us in displaying the image. Now if you come back to this image, and if you see the number of chessboard pieces, you can see that it has about 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 boxes on the horizontal, and if you count this 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 boxes on the vertical as well. So it has it's an 8 by 8 image, And you can see that that's something you need to specify, because what the algorithm is doing is it's trying to reflect what you know about the image. You know that it's a high contrast image, you know the number of boxes are so, and you also know that the boxes are symmetrical, they are of the same width and height. So you know all these properties, and these properties are now going to be matched with the image processing aspect to see how much this property is being manipulated because of the distortion in the camera. So come down here and we specify that the number of corners or number of boxes in the X direction is 8, but since we are doing coding, and coding starts with index 0, so index 0 will be 8 minus 1, 7. Similarly, for the number of boxes that we have in the vertical direction, we have 8 boxes, but if you count it from 0, which is index 0, then it'll be 7 boxes in the vertical direction. And the image that we have here, this is the chess.png image that we will be using to read it. So let's read the image first. img is equal to cv2 imread. So for us to read the image, and we need to find the path for this one. So come here, click on this and copy path, and just come back here and paste the file, so we know what the image or where the image is located. So it can read the image for us, and if we just try to display it for our purpose, cv2 im show img, it should display the chessboard for us right here in the browser. So this is working so far. Now the next step for us would be to convert this image into a grayscale image, so that then when we send it to the next algorithm, it is just working with grayscale values with one matrix instead of the RGB matrix. So we say cv2 convert color, and this function in OpenCV can convert a RGB image or a BGR image into a grayscale image. So you need to specify what are you trying to convert, and we're trying to convert this image img, and we are going to be using cv2 color BGR to gray. So BGR to gray. So we are converting BGR to gray because OpenCV reads it in a BGR format instead of an RGB format. So you're just converting it into a BGR to gray image. Once you have the grayscale image, now you want to specify, or there is a function in OpenCV called as find the chessboard corners. And the purpose of this function is it goes through the whole image and then tries to do those lane detection or tries to do edge detection in the image, and then understand where the corners of this image are present. And once we have those corners, then we can identify how much the corners are getting distorted. So for that purpose, there is a function called as cv2 find chessboard corners, and we will initialize it by return flag and corners. So it will give us the return flag and the corners. Return flag is just to help us whether or not it functioned properly or not. So it's a Boolean variable which will be either true or false, and corners will be holding all the location of the corners for us, so the x and y coordinates of the corners. So once we have the corners, then we specify cv2 find chessboard corners. So there is this function called find chessboard corners, and you need to specify where you're trying to find the corners. So you're finding it in the grayscale image, and you also need to specify the number of actual boxes in the image. And in our case, we saw that it was 7 by 7. So we're just specifying nx by ny, or 7 by 7 ny, and you're now just specifying the flag, which is going to be none for our purpose, and we are not so much interested in that. So once we have the corners, then now we can go to the next stage, which is drawing the corners. So if ret is equal to true, so if the finding of chessboard corners worked out properly, then please go about change or drawing the corners. And for that purpose, cv2 also has a function for us called cv2 draw chessboard corners. and this function will take the image and then draw the corners for us. And in our case, we want to draw the corners on our original image, the BGR image, and we'll say IMG, and please draw the corners. And I have 7 by 7 or 8 by 8 or 8 by 8 boxes, so please draw the corners, and you need to specify the corners that we detected in the previous step and the red or the return flag that it worked out perfectly. And once we have all of that, then we can just simply display the image for us, and the image is IMG, and we just play. But once we play this, you can see that it's able to detect all the corners on the image and then try to find out the relation between the corners. So you can see that it's also linking the corners from each aspect to the other aspect. So this is nothing but understanding the differences or the distances between the corners so that we can understand how much it has distorted. It is also giving us the perspective of what's the distance between each edge of the corner. So you can see that these diagonal lines is representing how much the diagonal or how much of the corners are moving away from each other subsequently in the image, because if there is any kind of distortion. So this is a very neat application to how to calibrate the camera. Now, the knowledge that we have from this stage, we will use it in the next step to do a further reversing of the distortion in the camera.